A doubly circular linked list, DCLL, is a powerful dynamic data structure that combines the advantages of both doubly linked lists and circular linked lists, providing bidirectional traversal and eliminating null pointers at the ends. In this structure, each node contains three components: the data field, a pointer to the next node, and a pointer to the previous node, forming a circular chain where the last node points back to the first, and the first node points to the last. This circular and bidirectional nature makes insertion, deletion, and traversal operations efficient and flexible. Understanding how to create, insert, search, delete, and display elements in a doubly circular linked list is fundamental for mastering data structures and algorithmic design. To begin with, the creation of a doubly circular linked list involves initializing the list so that it is ready to store nodes. When the list is empty, both the head and tail pointers are typically set to null. When the first node is created, its next and previous pointers point to itself, establishing the circular nature even with a single node. This self-referential structure ensures that operations do not require special handling for end nodes, as every node's pointers lead to valid memory. Creating a linked list often involves defining a node structure with three fields: data, next, and prev. The creation phase may also include functions to allocate memory dynamically and set initial values. In a real-world scenario, the creation operation also ensures that the program can handle memory allocation failures gracefully, preventing undefined behavior. Once the first node is added, the list becomes active, and subsequent operations work around this initial configuration. The next important operation is insertion, which must support multiple cases to ensure the list remains functional in all situations. The major insertion types in a doubly circular linked list are insertion at the beginning, insertion at the end, and insertion at a specific position. To insert a node at the beginning, you must allocate a new node, assign the data, and then adjust pointers so that the new node becomes the new head of the list. This involves setting the new node's next pointer to the current head, its prev pointer to the current tail, and updating the tail's next pointer and head's prev pointer accordingly. Since it is a circular list, the last node's next pointer always points to the head, and the head's prev pointer points to the tail, ensuring continuity. Inserting at the end is conceptually similar but requires linking the new node after the current last node and updating the tail pointer. The new tail's next pointer must point to the head, and the head's prev pointer must be updated to preserve circularity. Inserting at a particular position is more complex because it requires traversal from the head to the desired position. Once the correct location is found, you adjust the pointers of the new node and its neighboring nodes to maintain the list structure. The flexibility of a doubly circular list ensures fast insertions because no shifting of elements is required, unlike arrays. Moving forward, the search operation allows locating a specific element within the list. Searching in a doubly circular linked list typically involves traversing the list from the head node and comparing each node's data with the target value. Because the list is circular, traversal must stop when you return to the head node, which prevents infinite loops. Searching can be performed using either forward or backward traversal, thanks to the prev and next pointers. Forward traversal is more common, but backward traversal can be useful when optimizing searches from the tail direction. Searching is a linear time operation, with a worst-case complexity of O(n), because each node must be examined until the desired element is found. The circular nature avoids null pointers, which reduces the need for boundary checks during traversal. In practice, a search operation may also return additional information such as the position of the element, a pointer to the node, or a Boolean value indicating whether the element exists. Following the search operation, the delete operation is one of the most important in the doubly circular linked list, and it must handle several deletion scenarios: deleting the first node, deleting the last node, deleting a node at a specific position, and deleting by value. Deleting the first node requires updating the head pointer to the next node, while ensuring that the new head's prev pointer is updated to the tail, and the tail's next pointer points to the new head. If the list contains only one node, deleting it results in an empty list where head and tail must be set to null. Deleting the last node requires updating the tail pointer to the previous node and adjusting the head's prev pointer accordingly. When deleting a node at a specific position, you must traverse the list to reach the correct location. Once the target node is found, its previous node's next pointer and its next node's prev pointer are updated to bypass the node being deleted. The memory occupied by the deleted node is then freed. Deleting by value involves searching for the node first and then performing deletion based on the node's location. The doubly circular nature simplifies deletion because there are always valid previous and next nodes as long as there is more than one element. Finally, the display operation allows visualizing the contents of the list. Displaying a doubly circular linked list usually involves starting from the head node and traversing forward until you return to the head. During traversal, you print or process each node's data. The circular nature ensures that traversal is continuous without encountering null. Displaying in reverse order is also possible by starting at the tail node and following the prev pointers. This backward traversal capability is one of the main advantages of the doubly linked structure. The display operation is particularly useful in debugging because it allows programmers to confirm that all pointers are correctly maintained and that circular links are preserved. Some implementations also display the memory address of each node, its prev pointer, and next pointer, which helps identify issues like broken links, incorrect pointer updates, or logical errors in other operations. When all these operations, create, insert, search, delete, and display, are combined, they enable full manipulation of a doubly circular linked list. This data structure is especially useful in applications like task scheduling, music player playlists, round-robin CPU scheduling, navigating browser histories, and any system requiring continuous cyclic traversal. Its ability to move forward and backward without boundary limitations makes it more versatile than singly linked or linear lists. The absence of null pointers reduces the possibility of pointer-related errors and makes algorithms easier to implement once the circular concept is understood. The robustness of a doubly circular linked list comes from its careful pointer management. Each operation must maintain the circular relationship between the head and tail nodes. Errors in pointer updates can break the chain, leading to infinite loops or inaccessible nodes. Therefore, the logic for modifying next and prev pointers must always be handled carefully. Another important aspect is memory management. Since nodes are allocated dynamically, it is essential to free memory correctly during deletion to avoid memory leaks. For large-scale applications, proper memory handling ensures efficient performance and prevents system crashes. Additionally, the time complexities of operations in a doubly circular linked list are predictable and efficient. Insertion and deletion at the beginning or end require constant time 1. Because they only involve pointer adjustments. Searching, displaying, and inserting at arbitrary positions require linear time. N. This performance makes the structure suitable for applications where frequent insertions and deletions are required, especially at both ends. The dual pointer structure allows flexibility but increases memory usage per node due to the extra pointer. However, the benefits far outweigh this overhead in most applications. The data structure provides balanced functionality that is not possible in singly linked or strictly linear lists. Its continuous nature makes it ideal for cyclic processes in computing. In conclusion, the doubly circular linked list is a highly efficient and versatile data structure that supports operations like creation, insertion, searching, deletion, and display with significant flexibility. The circular linking of the head and tail nodes eliminates edge case complexities and supports uninterrupted traversal. The bidirectional pointers enhance operational capabilities by allowing movement in both directions. Mastering these operations provides a strong foundation for understanding complex data structures and solving real-world computational problems that benefit from dynamic and circular data management.